Hello class, this is Dr. Anderson, and we are starting one of my absolute favorite topics, which is renal physiology. So this is the material for the first week, and I believe I will divide it into two parts. First of all, I'm going to give a review of the nephron and talk about renal blood flow. Then we'll take a break, and then I'll come back and get glomerular filtration and introduce the concept of clearance. All right, here's a picture of your kidneys. This comes from your textbook Vander. Notice that the kidneys are encapsulated. So there's a very thick capsule that goes around the kidney. Here we see a unit of the kidney called the nephron. We'll talk about that in just a moment. There's an inner part called the cortex, an outer portion called the cortex and an inner portion called the medulla. The thing here is that the cortex is isoosmotic or isotonic. It's about 300 milliosmolar. But when you move in towards the medulla, an interesting thing happens. The medulla is hyperosmotic. It's about 700 milliosmolar sodium chloride and 700 milliosmolar urea. And so there's an interesting thing happens that in the loop of Henle, here's the loop of Henle right here, as it flows through that hyperconcentrated medulla, it is very important for setting the stage of being able to concentrate the urine in the presence of ADH, or to let water go out into the urine if the body is well hydrated and it's not needed. So then fluid goes all the way through the nephron, and then when it enters the renal pelvis, it's now urine, which goes on its way to the bladder through the ureter. So here's a picture from a medical physiology textbook. I want to say it's Rhodes and Tanner. And this is a line diagram of a couple of nephrons. So we have a nephron that's kind of up in the cortex. A little bit of it dips into the medulla, a little bit of the loop of Henle. But up here in the cortex, we see a glomerulus. So notice we have a bunch of capillaries. There's about 20 capillaries in a capillary bed called the glomerulus. That filters material into a little cup called Bowman's capsule. Then we go through what's called the proximal convoluted tubule. Then down through the descending limb of the loop of Henle, the ascending limb of the loop of Henle. Then there's a distal convoluted tubule, and then we go into a collecting duct. The collecting duct that's in the cortex is called the cortical collecting duct. That joins with a collecting duct that goes through the medulla, which then we call the medullary collecting duct. Now, that's a cortical nephron. We also have some nephrons that are situated a little differently in the kidney. So again, here's the glomerulus. There's Bowman's capsule, proximal convoluted tubule. We're all in the cortex, but then we have this longer loop of Henle that dips way down in that concentrated medulla, a descending limb and an ascending limb. Then again, we've got the distal convoluted tubule, and that's going to make its way into the collecting duct. Then we have the medullary collecting duct, and so lots of nephrons are emptying into this collecting duct. So the cortical nephron's a little more superficial. The juxtaglomerular nephrons are a little more deep. And both, here you see, this is a piece of the distal convoluted tubule, and then this is the afferent arteriole. Together they form something called the juxtaglomerular apparatus. There's another one over here. And the juxtaglomerular apparatus is very important for intrinsic regulation. of filtration in the kidney. It's also the site of renin production and a very important part of blood pressure regulation. Here's a light microscope section of the cortex. So we just looked at this diagram showing you nephrons, and there's all this space out here. But then you look at a light microscope section of the kidney and you see there's not really any space. Lots and lots of tubes all squished together. So here's the glomerulus. It's unfortunate that I'm working in red. Maybe I should switch to a different color of ink. So here's the glomerulus. Here's the glomerulus. There's when you think about the vasculature of the kidney, there's a renal artery that comes in. Then there's that divides into interlobar arteries, arcuate arteries, interlobular arteries, and then off the interlobular arteries we get these arterioles that are called afferent arterioles. They lead into the glomerulus. Then there's an efferent arteriole that leads into another capillary bed that you see all over the place in here, the peritubular capillaries. This is kind of interesting. It's a portal system. So you have an arteriole to a capillary bed, then another arteriole to a second capillary bed. So two capillary beds in series where you don't have to go through the heart. That's called a portal system. Other thing is, up in the cortex, you just see lots and lots of tubes. And so these are our proximal convoluted tubules and distal convoluted tubules that are all mixed up in one microscope slide. So these things are all packed in there. But then we have pictures like the one in your textbook. So again, we see cortical nephrons found mostly up in the cortex. And then our juxtamedullary nephrons that dip way down into the medulla. Now notice differences in the vasculature. So here's our interlobular artery. Then we have an afferent arteriole, a glomerulus, then an efferent arteriole, and then a capillary bed called the peritubular capillaries. Those are the capillaries around the tubules. Those are associated with those cortical nephrons. If we look at our juxtamedullary nephron, so there's the interlobular artery, there's an afferent arteriole, there's the glomerulus, the efferent arteriole, and now we have these kind of looping capillaries. This is called the vasa recta. Vasa recta. And those are only associated with these long loops of Henle with the juxtamedullary nephrons. And these will be very important for keeping the medulla concentrated and for setting the stage for the action of a hormone called ADH, antidiuretic hormone. So what does the kidney do for you? Oh my goodness, what the kidney does for you. All you have to do is look at a patient for whom the kidneys are not working to realize how wonderful the kidneys are. So the kidneys participate in a process called clearance. They basically filter all your blood, reabsorb essential substances that you want to hang on to, and secrete substances that you want to get rid of and put into the urine. The kidneys are very important for pH balance. So we've talked about the lungs, now we're going to talk about the kidney, and then after that we're going to integrate that together to talk about pH balance. Kidneys are very important for water balance, helping you save water when you need it, for electrolyte balance, so important for absorbing sodium and calcium, for regulating potassium, absorbing magnesium, absorbing phosphate, all those electrolytes, very important in the kidney. Plus, your kidney makes things. So it makes an enzyme called renin. That's a very important gateway to the renin-angiotensin system. it makes a cytokine called erythropoietin. Erythropoietin is produced with renal hypoxia. Erythropoietin then stimulates the release of red blood cells from the red bone marrow. So that's a negative feedback mechanism to regulate the hematocrit. It helps produce a metabolite of vitamin D called calcitriol, which is important for calcium metabolism. And it makes a whole host of signaling agents, prostaglandins and bradykinins. So cleaning your blood and making urine requires these three processes. First, you have to filter your plasma. And that happens between the glomerular capillaries, shown here, and Bowman's capsule. It's kind of like if I think about cleaning my son's room. My son's room gets so messy at some point, I just take everything out of there. That's kind of like filtration. And then I look at some of the things in his room and I think we need to throw these away. And so I carry them out of his room and put them in the trash. I secrete substances. Or I might say, oh, okay, so these are his clothes, these are his sneakers, these are his notebooks and his art supplies. Those things we want to keep, and we put those back in his room. That's like reabsorption. So secretion is a process where we add wastes to the filtrate to eventually go out in the urine. Reabsorption is a process where we take substances from the filtrate and put it back in the plasma so we can hang on to it. If you look on our diagram here, this shows you what we do with potassium. Potassium actually does all three things. It's freely filtered, so it gets filtered. In the proximal tubule, potassium is reabsorbed. In the distal tubule and cortical collecting duct, potassium gets secreted. And so, what's filtered minus what's reabsorbed plus what you secrete ends up giving us excretion. We're also going to talk about how excretion is related to another concept called clearance. Excretion is about what's going out in the urine. Clearance is about the mils of blood per minute that are cleaned. So here we see the tube. Inside the tube is the lumen, and the lumen is surrounded by epithelial cells. So here we see an epithelial cell right here. This is called the luminal side of the cell because it's next to the lumen. Another term people can use is apical. I tend to use luminal just because it's a little more descriptive. The cells are connected by structures called tight junctions. So they're held into a sheet. And then we have the sides and the back of the cell. That's called the basolateral membrane. Then we have our interstitial fluid, and then we have our capillary with the plasma. So essentially, if a substance is crossing the luminal membrane, going through the cell, crossing the basolateral membrane, and then entering the plasma, that substance is being reabsorbed. However, if a substance is leaving the plasma, entering the interstitium, crossing the basolateral side of the cell, moving through the cell, and then crossing the luminal side of the cell to get added to the filtrate, that substance is being secreted. Since the tubular cells have the transporters that accomplish secretion and reabsorption, we can also talk about tubular secretion and tubular reabsorption. So here's a picture I drew with my paint program. I want you to think about all the transporters we've learned about previously. Notice on the basolateral side of the cell, we have a sodium-potassium ATPase. That is typically where that protein is found. It is using ATP to generate and maintain an asymmetric distribution of sodium and potassium. Notice on the luminal side of this cell, there's a sodium coming in as a hydrogen is moving out. This is a secondary active transporter. The energy from ATP is used to make a sodium gradient. Then the sodium gradient is used to transport hydrogen out of the cell. We tend to find this kind of thing in the first part of the tubule called the proximal tubule. Also in the proximal tubule, we see a co-transporter for sodium and glucose. So again, we use ATP to make a sodium gradient. We use sodium to make a glucose gradient using a secondary active transporter. This is called the sodium glucose transporter, or the SGLT. Once we create a glucose gradient, then we can use a facilitated transporter, or the GLUT transporter, for glucose to leave the cell and then go into the blood. So reabsorption of glucose is an important activity in the kidney. Later in the kidney, when we're adding extra hydrogen ion to the filtrate, we use hydrogen ATPase to get rid of the hydrogen. And we'll talk about that later on in the course. So I was thinking I was going to talk about this in the other presentation, but here it is. Clearance. I expect you to know the definition of clearance. I expect you to know the formula for clearance. I will not give you the formula on the exam. I will expect you to know it, and I will expect you to be able to use it on the exam. So the clearance of X is equal to urine flow in mils per minute, urine concentration divided by plasma concentration of X. How is clearance measured? Well, a patient is asked to collect a 24-hour sample of urine, and that could be in the hospital. You need a 24-hour sample because you're going to take a sample to get the urine concentration, and we want that reflected over 24 hours. And we're going to convert that 24 hours of urine into mils per minute. People don't pee in mils per minute. So you collect a 24-hour sample, and then you extrapolate back to mils per minute, and then you take a plasma sample. And so the lab could take these samples, calculate, measure these concentrations, and then calculate a clearance. Notice clearance is expressed in terms of plasma volume per time that is cleared of a particular substance. In other words, it's the mils per minute of plasma that no longer has X in it. So you clean your blood as you increase clearance. This is different than excretion, which is defined as how much stuff is going out in the urine. If you're clearing more things, you're excreting more. But clearance is expressed in terms of plasma. Excretion is expressed in terms of urine. It's important to distinguish that. So we need to start out with the renal plasma flow. We're going to have blood entering the kidney, and the liquid part of that is the plasma. So you send about 1 to 1.3 liters of blood to your kidney per minute. That's 20 to 25% of the cardiac output. That's a lot of blood. If we index that by weight, it's 4 mils per minute per gram. That's more blood than your brain gets. So why are the kidneys getting so much blood? Well, the kidneys have a lot of transport activity. The kidneys have a high ATP demand, and the kidneys clean your blood. So if the kidneys are cleaning your blood, it makes sense that you would send a lot of blood to the kidney. So how do we measure renal plasma flow? Well, we're going to need a couple of things. We're going to need the clearance of an organic acid. Now, why is that? Because organic acids are freely filtered. They're filtered at the glomerulus, and they're fully secreted. So if you clean the blood you filter, plus you clean additional blood through secretion, you're basically cleaning all your blood. And what's all your blood? It's the renal plasma flow. So often nephrologists will do something called the clearance of PAH. And I've lost my little, there it is. PAH, or para-aminohippuric acid, which is about 92% secreted. So the renal plasma flow is not exactly equal to the clearance of PAH, but it's pretty close. There are other things. This is a contrast medium. This is an antibiotic. So things that are highly secreted will tell you about your renal plasma flow. Then what else do you need to know? You need to know your hematocrit. So if you know your renal plasma flow and you divide it by 1 minus the hematocrit, then you can work back to renal blood flow. Now, why do we care? Well, the renal plasma flow is going to end up being highly related to the glomerular filtration rate. The glomerular filtration rate is the rate at which you filter plasma from the glomerulus to Bowman's capsule. And it's very, very important that the glomerular filtration rate be highly regulated. You see, if your glomerular filtration rate is too high, you're creating more filtrate than your kidneys can reabsorb, and you won't be able to maintain your blood pressure. However, if your glomerular filtration rate is too low, you're not cleaning your blood, and you're going to have waste products build up in your body. So it's important that filtration be just right. So one of the ways we try to make sure that our renal plasma flow is fairly constant, so that our GFR is fairly constant, is through a process of autoregulation. So in the next few slides, I'm going to talk about why PAH measures renal plasma flow, and then I'm going to finish up with talking about autoregulation. So here's a graph about PAH. Notice my x-axis is plasma, PAH, in milligrams per deciliter. Notice that son of a gun. Then this is pH going out in the urine. So this is plasma, and this is urine. Somehow my urine got cut off. All right. So if the only way we got rid of PAH is through filtration, we would see that the greater the plasma concentration, then the greater the excreted concentration. However, we don't just filter PAH, we also secrete it. So we come in through the afferent arteriole, there's the glomerulus, there's the efferent arteriole. Some PAH is going to be filtered. And then the rest of the PAH is going to be secreted. Notice as the plasma concentration of PAH goes up, the more we secrete. And then we level off because we've reached something called the transport maximum. Well, secretion is an active process, and it requires a transporter. What happens when all your transporters are occupied? You've reached the maximum rate of secretion. So if all your transporters are working, you can't increase your secretion anymore. So notice that if you look at total excretion, and remember, excretion is a combination of secretion and filtration. If you look at excretion, while we're able to increase through secretion, we have a really high slope of excretion increasing as we increase plasma levels. But then once we reach our transport maximum, we can still keep excreting, but at a lower level, because now we're only adding to excretion by filtration. So when we measure the clearance of PAH, we're going to get what's called an effective renal plasma flow. And if we say pH is about 90% cleared, then we can take the clearance of PAH, divide by 0.9, and then correct up to a corrected renal plasma flow. What about autoregulation? Well, autoregulation keeps the renal plasma flow fairly constant. Therefore, we can keep the GFR fairly constant, even though renal pressure is changing. So here's what we see. Our x-axis is mean arterial blood pressure. Notice it's 40, 80, 120, 160, 200, etc. Now, notice before 70 or 80, so I've always been taught 70. This particular graph shows 80, but somewhere around 70 or 80. Below this, this totally follows Ohm's law. If you increase your pressure gradient, you're going to increase your flow, given that we have a given resistance. So you see an increase in flow as we increase our pressure gradient. And then we get to a point where it kind of levels off. How can we be increasing the pressure gradient but keeping the flow fairly constant? The only way to explain that is resistance is increasing. So autoregulation is a process by which the afferent arteriole constricts, increasing renal resistance so that the flow doesn't go up. So if you think of Ohm's law, and we have flow is equal to delta P over R. If we increase the pressure, but flow stays the same, the only way to explain that is resistance is going up as well. And that's exactly what happens. We find that the afferent arteriole constricts, preventing the blood flow from going up. Now, how does that happen? There are a couple of schools of thought about that. One is that as you increase pressure and flow, you wash away vasodilators and you get contraction of the afferent arteriole. There's another theory that there are stretch-regulated receptors in the afferent arteriole. When you stretch the afferent arteriole, those stretch-gated channels let in calcium, and then the vessel reflexively contracts, and there's probably more evidence for that second one. Okay, I'm going to stop here. We've sort of given an overview of what's going on the nephron, talked about the functions of the kidney, talked about the blood flow to the kidney, and a little bit about autoregulation. In the next presentation, we're going to talk more about filtration. We'll talk a little more about other intrinsic methods. I should say that autoregulation is an intrinsic mechanism because you can take, say, a kidney out of a rabbit, change pressures, and you'll see autoregulation of flow in an isolated perfused kidney. That means you don't need a nerve and you don't need a hormone. So it's intrinsic to the kidney. All right, I'm going to end it for here, and I'll talk to you again in the next presentation.